And what I want to do to conclude this part is just to show you some example inference rule that would be useful for this week. Okay, I'm gonna maybe add more inference rule to our example list as we go. Right, let's talk about, I think I got about 3 slides of inference rule to go over with you, right? Let's talk about it. Okay, so the first one here will be the piano theorem axiom number 1, right? We're saying that without any hypothesis, 0 is a natural number. All right, so that's the first one. 0 is a natural number. You don't need any justification for that. You can, as long as if you can actually get to this particular get to this particular sequence, in that case, it can just be proved automatically. All right, piano theorem number 2, which is something we just talked about, right? n plus 1 is a natural number, assuming that n is a natural number. So this part, the sequence here, is automatically an axiom, or automatically a theorem. You don't need to provide any further justification. And there's a variant to piano theorem number 2. I would just call that P2 prime, which might also be very useful. We're saying that n minus 1 is a natural number, given that n is positive. That also makes sense. And you can also claim that this sequence is automatically proved without any further justification, right? You can see all the inference rule I actually present in this particular slide, they actually got a flavor where the antecedent is simply just empty, right? It would be as if we simply don't need to prove anything else. We just prove true, which requires no work, right? Right, the final one, it's a piano theorem or axiom number 3. We're saying that n is larger than equal to 0, assuming that n is a natural number, right? This one is also quite obvious. And if you recall what we did in lab number 1. In lab number 1, in context C0, remember we declared some axiom over there to say n, I believe we said C, credit limits. Credit limits is a natural number. And we want to declare something else as a theorem to say 0, n should be larger than or equal to 0. And that can be automatically proved exactly because of P3, right? Because to prove this, we just have to know this is true. And in our lab 1 model, n is a member of natural number is declared as an axiom, so that's assumed to be true. So that's why that particular theorem n is larger than equal to 0 is automatically proved, right? I want to draw some connection. All right, so that's about the axioms for the inference rule that we can use, right? As if you can manage to really make sure the outstanding sequence can somehow be transformed into any one of these, in that case, you're proved for the sequence. That's something we'll see. All right, so let's see the second page for the examples inference rule. So this one is also an axiom. So we are saying that n plus 1 should be less than or equal to n, assuming that n is strictly less than n. Let's take some example here. For example, if I know 4 is less than 5, right? 4 plus 1, which is 5, is still less than or equal to 5, right? That's kind of the edge case over here, right? So this increment rule is also very useful. You can definitely read through the written description as well. But what I want you to do is to really make sure you know what's really going on over here, right? Again, the consequent over here is a sequence. So we are saying that if your sequence that's outstanding has this particular form, that means that sequence can be proved automatically without any justification. And that particular thing we are proving is, we're saying that n plus 1 less than or equal to n, assuming that n is strictly less than n. That's what we're doing. The second one is kind of symmetric. So we're saying that n minus 1 is strictly less than n, assuming that n is less than or equal to n. For example, let's say this. Let's say 4 is less than or equal to 4, right? In that case, 4 minus 1, which is 3, is now strictly less than 4, right? That's how you you can exemplify the inference rule or the sequence over here, just to see how it works, right? That's just the informal text just to explain it, right? Hopefully so far so good. So I don't think there's really much I need to say about each individual rule. They're rather straightforward. If there's any more complicated one, I'll definitely try to illustrate, but I think these one are the elementary one, okay? Of course, if you got any trouble understanding them, reach out to me. All right, the final page over here, let's say this. Monotonicity, right? We talk about it. We're saying that to prove to prove G, assuming that H1 and H2 are true, right? It will be sufficient to prove the same goal G under less hypothesis, just H1. We can drop hypothesis. That's what we did earlier. And this one here, don't be too scared by the form. It's actually rather simple over here. Let's think about what's going on here. Let's think about it in the big picture. We're saying that to prove this particular sequence, it will be sufficient to prove this sequence over here and also this sequence over here. So that's why we said before in the earlier slides, whenever you apply any inference rule, you're going to transform a single sequence in the consequence into a set of sequence, which might be 0, might be 1, might be 2, and etc. Independently, right? Again, to prove this sequence over here, to prove this single sequence, it would be sufficient to prove this and prove this independently. All right, let's try to go dive in, deeper into it. We're saying that to prove R, assuming that some hypothesis H and also another hypothesis, which is more like a disjunction, it would be sufficient to prove the same goal, which is R over here, but under either the left disjunct, or sorry, the right disjunct over here, or under the assumption of the left disjunct over here, right? We're basically splitting the disjunctive assumption over here into P here and also Q here. That's what we're doing. But why does this inference rule work, right? I would like to give you a little bit of justification over here. It's actually involved a little bit of proof on the predicates. Maybe you have done that earlier, right? Let me show to you quickly, okay? Right, so that's the rule we just talked about over here. And again, let me just highlight the part that's really important. We got a disjunctive assumption over here, and we got the right disjunct, we got the left disjunct over here. For the for simplicity, let's just not worry about H for now, right? It's simply just any additional hypothesis. You simply don't drop when you do the transformation, right? Remember what we said about nested implications for the meaning of inference rule. So what would this be in this case, right? I think about it. In the case of the top over here, if I got this part over here, it will be basically two sequence to be discharged, right? So that means this and this. This must be discharged and this must be discharged. The left one will be P implies R, and independently Q implies R, right? If I can prove this, that means I would have already proved this, because to prove this, it would be sufficient to prove this, right? So both, you should really know the informal meaning for inference rule pretty well by now, right? So this means that will imply, right? You can think about this implication here corresponding to the horizontal line over here, and it will be the disjunctive hypothesis over here implies R. Right, so that's really what we have over here, right? So how do we actually prove this, right? We can actually prove this quite easily. Okay, let's now take a look, right? What I can do is I can start with maybe this one here. I can start with this. Let me start with this, okay? So I would say P implies R, and also Q implies R. And remember one of the theorems that we spoke about the definition for implication in the math review lecture, right? So this is more like an equivalent style of proof. We say it's equivalent to some other predicates. In the middle, we put some justification steps by quoting maybe some theorem or axiom that we know about. Definition of implication, which is whenever we say P implies Q, that's equivalent to not P or Q, right? That's something we did earlier, right? So this is a justification. Let me highlight it over here. So by using this justification, we got another equivalent predicate, which will be not P or R. Right? I'm going to apply that twice. And also not Q or R over here. Right? And I will be able to apply another thing, which is called the distribution of distribution of or over n. Okay. Definition of distributing or over n. Okay, what does that mean? So if I actually got, for example, P or Q and R, that's equivalent to P or Q and P or R. Right? If I want to distribute P or over this particular conjunction, so that'll be P or Q and P or R. Right? That's exactly what you did earlier, right? I'm gonna assume you actually are okay with that. Okay, so this is another justification. You can see this part over here is exactly matching the right hand side, so we can simply do the equivalent to the left hand side. More precisely, you can, okay, so what you really want to make sure you do is to match this particular part to this part over here. Of course, we got PQR, we also got PQR. You just have to distinguish between which P and Q I'm talking about, right? Let's try. Okay, it's not too bad. Okay, so let's say here, so what we have is, you can think about the P here and the P here, right? The same P is really corresponding to the R over here, right? And then the Q here, the R here is really corresponding to this one here and also this one over here, right? And what should that be equivalent to? That should be equivalent to this, right? Which would be over here. Let me write it down. So that would be basically P, which would be the R, right? Or and Q and R, which would be not P and not Q. All right, something like that. Okay. And also, if you remember De Morgan, right? If I actually got not P and not Q, it's exactly equivalent to the following, right? So let me just, I'm running slightly out of space, so I'll just make it smaller. I really want to show you in one continuous block. Okay, let's say we got here. Okay, we're getting there, right? And if you remember De Morgan, which is about, if you actually got negation over P or Q, that's equivalent to not P and not Q, right? It's definitely something we reviewed earlier. That's a very useful theorem to use. This part here is matching this part over here, so it should be equivalent to not P or Q, right? And also, let me swap the order, right? Of course, we also got some commutativity of conjunction, but for now, let's now skip that step. So we're gonna have not P or Q or R. And we are basically getting there, right? Because this part over here is indeed equivalent to that, according to the definition for implication, right? So let me just do one more. So this should be equivalent to, and let me put the steps over here. Definition of implication. The same definition, so I wouldn't repeat it. In that case, it's going to be, you can see this part over here implies R. So that'll be P or Q implies R over here, right? Basically what we have shown over here, that's the justification. And if you look at the very beginning and the very end, we basically have shown that this part over here is equivalent to this part over here. They are just equivalent. So of course implication will hold as well. All right. It's a very quick justification about if you actually got, for example, intuitively, if you want to prove something under some disjunctive assumption, it will be equivalent to, if you, well, in this case, equivalent simply means more than sufficient, right? It would be sufficient if you simply try to prove the same R under either the left disjunct or the right disjunct over here, and then prove both one conjunctively, right? That's what we are saying, right? So look at this justification here. I think it's rather useful, and also for you to review, warm up a little bit about how to do equivalent style proof. Okay, again, equivalent style proof. Start with something you want to prove, and every time you do some transformation, you want to make sure you apply certain justification, right? I'm just showing to you exactly the example you can use, all right? Already, that's about the inference rule for this particular one over here. It's called the or and then left, meaning that we talk about, so the left over here, we're talking about it's really to the left of the turnstile. So that's why it's saying the left. And we're talking about the one of the hypotheses being disjunction, all right? Right, you can also look at the written text as well. And two more. And here we are talking about R means that we are talking about to the right of the turnstile, right? If the goal is really to prove some disjunction, right? Meaning that we want to prove that either this is true or this is true. It makes sense. It would be sufficient if we only prove one of them, right? In order to prove that a disjunctive goal is actually true under certain hypothesis, it would be sufficient to prove under the same hypothesis that the left disjunctive goal is actually true, right? Symmetrically, you can see here we got R2 over here. Again, R over here stands for to the right of the turnstile. That's what we are trying to transform. And if you want to prove some disjunctive goal, it would be sufficient if you try to prove just the right disjunct, either to prove the left disjunct or the right disjunct over here, right? Either one, right? So that's why it's 1 or 2 over here. Alrighty, so that's about the inference rule I would like to talk about. That'll be sufficient just for this week's lecture. Later on, if there's any additional rule that we need to introduce, I'll list them just for your convenience. And if you look into the notes over here, I'm including this clean page over here, which you can download, keep it handy, right? So these are the rules that we're going to use for the following part of the lecture to really go back to our initial model and see how we can discharge all the 4 sequence for invariant preservation.